This conversation is powered by Google Illuminate. Check out illuminate.google.com for more.
Welcome to the discussion. Today's paper, Fully Automatic Neural Network Reduction for Formal Verification, tackles a critical challenge in deploying neural networks in safety-critical applications: scalability of formal verification methods. The authors propose a novel approach to reduce the size of neural networks while maintaining the soundness of verification. What are the key limitations of existing formal verification methods for neural networks that this paper addresses?
Existing methods struggle with the computational cost of verifying large neural networks, especially under strict time constraints. The problem is inherently complex. Verifying ReLU networks alone is NP hard. Current approaches, whether optimization-based or using reachability analysis, often face scalability issues when dealing with real-world networks used in safety-critical systems. The verification time becomes prohibitive, especially when many instances need verification, as in video processing or real-time control systems. The paper mentions both optimization-based and reachability analysis-based verification methods. Can you elaborate on the differences and why the authors chose a reachability analysis approach?
Optimization-based methods often relax the nonlinear activation functions into linear constraints, solving the relaxed problem using linear programming or SMT solvers. Reachability analysis, on the other hand, propagates sets through the network, providing an enclosure of the output set. The choice depends on the trade-off between precision and computational cost. The authors opted for reachability analysis with zonotopes, likely due to its ability to handle nonlinearity more effectively than simple interval arithmetic, while remaining computationally tractable compared to more complex set representations like Taylor models or star sets, especially for large networks. The soundness of the reduction is crucial, ensuring that verification of the reduced network implies verification of the original.
The core of the paper is a sound neural network reduction technique. Can you explain the intuition behind this method and how it achieves soundness?
The intuition is that many neurons in a layer behave similarly for a given input, especially near saturation points of activation functions like sigmoid or 10. The method identifies groups of similar neurons, merge buckets, and replaces them with a single neuron, effectively reducing the network size. Soundness is maintained by carefully bounding the approximation error introduced by this merging process. This error is incorporated into the calculations of subsequent layers, ensuring that the verification of the reduced network provides a sound guarantee for the original network. The paper uses zonotopes for set representation, but the approach is adaptable to other set representations.
How does the algorithm determine these merge buckets and the appropriate tolerance for merging? Is it a manual process or automated?
The algorithm offers both static and dynamic methods for initializing merge buckets. Static buckets are based on the asymptotic values of the activation function, e.g. 0 and 1 for sigmoid. Dynamic buckets use the centers of the output bounds of each neuron, clustering similar neurons. Crucially, the tolerance that defines the similarity threshold is automatically determined using a binary search algorithm aiming for a user-specified reduction rate while ensuring verifiability. This automation is a key contribution, making the method practical for real-world applications.
The paper highlights the on-the-fly nature of the reduction. What are the advantages of this approach compared to reducing the network beforehand?
Reducing the network on the fly avoids the computational overhead of propagating high-dimensional sets through the entire original network before reduction. The algorithm uses a one-step look-ahead with interval arithmetic to efficiently estimate the output bounds needed for merging, significantly reducing the computational burden. This is particularly beneficial for complex set representations beyond zonotopes.
The paper demonstrates the applicability of this method to convolutional neural networks. How does the approach adapt to the specific structure of CNNs?
CNNs exploit the spatial locality of image data. The authors leverage this by explicitly considering the similarity of neighboring pixels. Convolutional layers are treated as linear layers with shared weights, allowing the reduction method to be applied directly. The dynamic bucket approach is particularly effective for CNNs as it can identify and merge neurons representing similar image regions. The paper also introduces a sound image compression pre-processing step that further reduces the input dimension before verification.
The paper discusses reusing the reduced network for different scenarios. Can you elaborate on these scenarios and how the reduced network can be reused?
The reduced network can be reused in several ways. First, it can be integrated with branch and bound verification strategies, where the reduced network is applied to subproblems created by partitioning the input space. Second, the reduced network can be exported and used with other verification tools as the approximation error is handled explicitly. Third, in closed-loop verification, if the system's state remains within a certain region, the same reduced network can be reused for subsequent time steps, significantly speeding up the verification process.
The evaluation section shows impressive results. Can you summarize the key findings regarding the reduction rates achieved and the speed up in verification time?
The evaluation demonstrates significant reductions in network size and verification time across various benchmarks and network architectures. Reduction rates of up to 90% were achieved without compromising verifiability, particularly for CNNs. The overall verification time, including the reduction process, was reduced by up to 96% compared to state-of-the-art tools like A-Crown. The approach is shown to be effective for networks with various activation functions, ReLU, sigmoid 10A, and significantly larger than those considered in previous sound reduction work.
What are the limitations of this approach, and what are potential avenues for future research?
While the results are promising, the effectiveness of the reduction depends on the specific network architecture, activation functions, and the properties being verified. The approach might not be as effective for networks where neurons exhibit highly diverse behavior. Future research could explore more sophisticated methods for identifying similar neurons, potentially using more advanced clustering techniques or incorporating information about neuron sensitivity. Extending the approach to recurrent neural networks or other network architectures would also be valuable. Investigating the impact of different set representations beyond zonotopes is another promising direction.
The paper mentions the use of zonotopes. Could you briefly explain why zonotopes are a suitable choice for this type of analysis?
Zonotopes are a good choice because they offer a balance between computational efficiency and the ability to represent uncertainty. They're closed under linear transformations and Minkowski addition, making them suitable for propagating uncertainty through linear layers of the network. While the propagation through nonlinear layers requires outer approximation, the structure of zonotopes allows for relatively efficient computation of these approximations. More complex set representations might offer tighter enclosures but at a significantly higher computational cost, making them less suitable for large networks.
The paper emphasizes the importance of verifying neural networks in safety-critical applications. Can you elaborate on the implications of this work for such applications?
This work directly addresses the scalability bottleneck in formally verifying neural networks, making formal verification more practical for safety-critical systems. The ability to significantly reduce the size of networks while maintaining soundness allows for faster verification, enabling real-time verification in time-critical applications like autonomous driving or robotics. This increased efficiency could lead to wider adoption of formal verification methods, improving the safety and reliability of AI systems in these domains.
The authors mentioned that their approach is applicable to various activation functions. Does this mean there's no need for specialized techniques for different activation functions?
The core approach is agnostic to the specific activation function. The reduction relies on the output bounds of the neurons, regardless of the activation function used. However, the choice of merge bucket initialization, static or dynamic, might be influenced by the characteristics of the activation function. For example, static buckets are more suitable for functions with clear saturation points, while dynamic buckets are more adaptable to functions without such clear saturation.
In summary, this paper presents a significant advancement in the field of neural network verification. The fully automated sound reduction technique offers a practical solution to the scalability challenge, paving the way for wider adoption of formal verification methods in safety-critical applications. Thank you for this insightful discussion.